So I want you to forget everything you think you know about cybersecurity. That it's just a bunch of abstract code on a screen. Today, we're going to pull back the curtain on this high-stakes digital world. And honestly, it's part heist movie, part grandmaster chess match, with attackers and defenders locked in this constant, invisible battle. We're going to break down the entire anatomy of a cyber operation. Okay, so here's our game plan for cracking this whole thing wide open. First up, we'll map out the digital blueprint of the target. Then, we're going to uncover the secrets that are locked away deep inside the system. After that, we'll open up the hacker's playbook to really get inside their heads. Then we'll pivot and look at it from the other side. How do you build a digital fortress? And finally, we'll take a peek into the future at the unseen battlefield that's emerging right now. If you want to understand how a bank heist works, the first thing you need is the building's blueprint, right? Well, it's the exact same thing in the digital world. Before we can even start talking about attacks or defense, we've got to understand the absolute fundamentals of any network. It really all starts with something called a socket. Here's a simple way to think about it. Imagine an IP address is a building's street address. A port number? That's a specific numbered door on that building. A socket is simply the combination of both, the exact address and the exact door. That's the endpoint where all communication actually happens. So how does data actually travel through those digital doors? Well, there are two main ways. First, you've got TCP. Think of this like sending a certified letter. It's super reliable, and it makes sure every single piece of data arrives in the correct order. On the other hand, you have UDP. This is more like sending a postcard. It's way faster, but it doesn't guarantee delivery. This is actually perfect for things like live streaming or online gaming, where raw speed is way more important than perfect accuracy.
Okay, so now that we've got the blueprint, let's talk about what's actually inside the vault, our data. And protecting these valuables requires some pretty powerful digital secrets. It's a whole practice known as cryptography.
The bedrock of protecting digital secrets is something called hashing. It's kind of like creating a unique, completely irreversible fingerprint for a piece of data. You can take any message, literally any size, run it through a hash function, and you get back this fixed size string of characters. And here's the key, you can't go backward. You can never get the original data from the fingerprint, which is exactly why it's so critical for storing things like passwords securely.
But, and this is a big but, not all hashes are created equal. For a hash to be truly secure, it has to meet three really strict criteria. 1, it has to be one-way. You just can't reverse it. 2, it has to produce a fixed length output no matter how big or small the input is. And 3, it's got to be collision resistant, which is a fancy way of saying it's basically impossible for two different inputs to ever produce the exact same fingerprint. So one of the most brilliant tricks in all of cryptography is the Diffie-Hellman key exchange. It lets two people, we always call them Alice and Bob, create a shared secret key over a totally public channel like the open internet, and anyone listening in just can't figure it out. It works by them mixing some public numbers with their own secret private numbers. And through this process, they both magically arrive at the exact same secret key. It's like agreeing on a final pint color by only showing each other public mixtures. It's just pure mathematical magic.
All right, we've seen the blueprint, we've seen the vault. Now let's switch things up. It's time to put on the black hat for a minute and open up the attacker's playbook to see exactly how these digital heists are planned and pulled off step by step. Every trade has its essential tools. For a network attacker, something like Scapy is the digital version of a master locksmith's kit. It lets them craft custom network packets totally from scratch. They're essentially creating custom keys to send, to sniff, to probe a network, basically testing every single lock they can find, looking for a weakness.
A real cyber operation is nothing like a smash and grab you see in movies. It's this methodical, multi-phase mission. It starts off really quiet, with planning and reconnaissance. Then it moves into actively scanning for weaknesses, before you get to the actual exploitation. But getting in, that's just the beginning. After that, the goal is to maintain that access, all while staying hidden. Now for the good guys, the ethical hackers, there's one last critical step, reporting everything they found to help build stronger defenses.
The reconnaissance phase, it is all about casing the joint. An attacker is just quietly gathering as much intelligence as they possibly can. This involves passive stuff, like digging through public records and social media. That's what we call open source intelligence, or OSINT. And it also involves active techniques, like scanning the target's network to find open doors and windows, or in our case, open port.
This is it. This is the moment of entry. The safe is cracked.
Attackers use frameworks like Metasploit, which are basically these giant toolkits of prepackaged exploits, to breach a system. But getting in is just the first step. The real goal is to escalate privileges, to turn a standard normal user account into a powerful administrator with the keys to the entire kingdom.
Okay, so how in the world do you stop all this? Let's flip the script. Let's take off the black hat and switch to the defender's perspective. It's time to look at how they build and guard the digital fortress against these kinds of really methodical attacks.
You know, effective defense isn't just about building strong firewalls. It's about having a solid plan for when those walls inevitably get breached. The NIST framework gives us this structured, four-step playbook for responding to an incident. First, you prepare before an attack even happens. Then, you detect and analyze it when it does. Next, you contain the breach and get rid of the threat. And finally, and this is so important, you do a post-incident recovery to learn from what happened and improve your defenses for next time.
One of the most clever defensive tactics out there is actually active deception, setting these digital traps called honeypots to lure attackers in. This can give you super early warnings and some amazing intelligence on what an attacker is trying to do. But it's a trade-off. While honeypots are powerful, they take a ton of effort to manage, and they can even get you into some tricky legal situations if you're not careful.
This intense cat-and-mouse game of cyber offense and defense, it never, ever ends. The battlefield is constantly shifting under our feet. So let's look ahead for a minute at the next-generation ideas that are shaping the future of digital security as we speak.
Zero Trust architecture is a complete paradigm shift. It totally throws out that old-fashioned model of, a trusted internal network with a hard outer shell. In a Zero Trust world, there's no such thing as inside or outside. Every single request to access anything is treated like a potential threat and has to be rigorously verified every single time. No exceptions.
And here's how it works in practice. It follows three core principles. It starts with least privilege access, meaning you only get the keys to the rooms you absolutely need to be in and nothing more. Then comes continuous verification, constantly checking your ID, making sure your device is secure. And finally, dynamic policy enforcement, which means the security rules can literally adapt on the fly, changing based on new threats or if you start doing something unusual.
All right, prepare yourself, because this next concept sounds like it's straight out of science fiction. It's called homomorphic encryption. Just imagine sending your most sensitive, locked-down data to a cloud service. That service can then perform incredibly complex calculations on your encrypted data and send you back an encrypted result, all without ever having the key to see what was inside. It means we can process secrets without ever revealing them. It's just mind-bending.
And this really brings us to a profound question for the future. As technologies like homomorphic encryption get better and more common, our ability to both protect and use our most sensitive information is going to be completely transformed. So we have to ask ourselves, how will our very definition of privacy change? That's the question to think about as this unseen battlefield just continues to evolve.